Okay, thank you so much for being here. It's my great pleasure to host you here today. Prova. 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 Okay, so we're now ready to start. Again, thank you so much for being here. It's a pleasure to host you here. I'm Maria Grazia Dottoli. I'm the chair of the Decision and Control Laboratory, who is organizing the talk today, and I'm happy to have Professor Ishii. Welcome. It's our great honor. I also happen to be the president of SIDRA, which is the Society of Researchers and Professors in Education in Italy. It's also, and so I say this just for young people. If you're interested in continuing your studies in education, join us at the lab, and our pleasure to have new young people. Okay, so thank you again for being here, and I will just leave the floor to Professor Carli, who is the secretary of the Control System Society chapter, Italian chapter, and he will introduce the seminar. Thank you so much.
Thank you, Maria Grazia, for nice introduction. It's a very pleasure to welcome you in my role of Secretary of the CSS Italian chapters, and also on behalf of the other officer, I'm very happy to host this magnificent event today. In particular, we have today the colloquium Roberto Tempo in Automatica, and this is the 6th edition, and from some year, this event is spread throughout Italy. In particular, this year is here in Bari. And I do not personally, didn't personally know Professor Tempo, but I know from other people his magnificent work. So it's very, very important to us today to tribute to him through a distinguished talk from Professor Ishii. His seminar is about resiliency in multi-agent consensus under adversarial attacks. And we spent just a few words about Professor Ishii, that is a fellow both from IEEE and IFAC. His curriculum contains several stuff, as you can see in this slide. In particular, he's a full professor for University of Tokyo currently, and he was vice president for the IEEE Control System Society, and is also chair of some committee in the IFAC Association. And he was the EPC chair for several international conferences organized by IEEE and IFAC. And he was the recipient of the Control System Magazine Outstanding Papers in 2015. His seminar is about resiliency in multi-agent consensus under adversarial attacks. I now pass the floor to him for his speech, for his talk. Thank you so much.
Thank you so much for the kind introduction. My name is Hideaki Ishii. It's a great pleasure and honor to be here to give this talk for the Colloquia Roberto Tempo in Automatica. I understand that this is a seminar series that has been held in memory of Roberto, who has been a very close friend and colleague over many years. And I'm very grateful to be part of this seminar today. And also, before coming to Bari, which is a very new place for me, never been to the southern part of Italy. I also spent a few days in Torino with Fabrizio Dabene and colleagues, where I met Roberto many times, and it gave me some time to think about days spent with him. So, and today I'll be talking about some research which actually started while I was working with Roberto, and it has continued until now. So I'm very grateful to him for this reason as well. But I'll start with a few pictures in memory of Roberto, and I'd like to very much thank him and also his wife Christina for being a very warm, close friend over many years. In fact, I met him when I was a postdoc at the University of Illinois. This was in 2002 or so. I was a postdoc, and Roberto, his family came to visit there for half a year or so, and we immediately started collaborating. He gave the lecture on randomized algorithms for uncertain systems at the time. I took the course, which introduced me to probabilistic approach. My background until then was more hardcore robust control, where there was no room for probability. So it was all new. And he has been, since then, we've been working almost continuously for 15 years on different problems. And he's been a very great role model for me of research, not only for research, but also for being active in the Control System Society, for example, at the international level. I learned a lot by working with him. This is a picture from, I guess, one of the highlights of our collaboration. And we worked on this problem on randomized distributed computation approach for the Google search engine algorithm, which is known as the PageRank algorithm. And we had this, we had several papers on this, but for the article that appeared in the Control System magazine, we received the funding paper award. And it happened that Fabrizio was the vice president at the time. So he was the one who handed the certificates to us. And this was in 2015. nice moment. Yeah, that's right. Yeah, so this is one of the few pictures with Fabrizio and Thais, or Roberto also. And he had a lot of collaborations with people in Japan, including Yasumasa Fujisaki in the middle of the picture next to Roberto. And then he promoted a lot the collaboration between the Italians and the Japanese. So this was one visit that a lot of us came to Torino and visited some of the research institutes in Torino. And we had a workshop, and Professor Isidori was there as well. And he was a frequent visitor to Japan. So this is one picture with Professor Shinji Hara. We went to a small island in the Tokyo area. So we had a lot of good times over the years. And so this is one of the papers related to my talk today. So it's a paper from 2007, and on like an overview on randomized algorithms. So by then, Roberto had the book with Fabrizio and also Giuseppe Carafiore. So probabilistic approach in system control has been established as a viable and important tool by that time. And as you may know, randomized algorithms, it's an algorithm where you make random choices while you execute the algorithm. And this can help to make things either efficient, or sometimes it's really necessary to accomplish certain tasks. So it's an interesting area. And there are a lot of, so for this paper, we went through some of the research results from the past, and we gave some survey, and it was interesting because it opened up for us several different directions going beyond the randomized algorithms that was part of their book. And in particular, we found several distributed algorithms where randomization is really important and useful. And so in particular, I'll be talking about this so-called Byzantine agreement, and also gossiping in agent systems. And this is related to what I'll be talking about today. It's a little bit, looking back, it's interesting that since I've been working a lot on multi-agent systems over the past 10, 15 years, but this was really the starting point for me, because multi-agent systems started around early, well, maybe 2003 or 4. And by this time, I thought, I don't know how Roberto felt actually, but I thought we were like kind of a latecomers, because it was very popular. A lot of people were working already at the time. But then I thought that with this technique of randomized algorithms, maybe this is a good way to come into this field. And actually, that's, I think, what happened. So let me briefly explain this problem known as the Byzantine agreement problem. This is a problem in computer science. And it's started in the early 1980s. It's a classical problem related to faults in distributed computation. And it can be explained in a very interesting way, in like a story. So this is a picture that appears in the Wikipedia, I think. So the story goes like this. So we have several generals who are trying to attack the city. Maybe this is in the Byzantine city. Anyways, so they want to decide when to attack and they want to do this all together, right? So to decide when to attack, they exchange messages among themselves. And the message is going to contain either let's attack or let's wait. Okay, so it's a binary decision problem. And then everybody's going to exchange this. And then once you collect all the messages, each general will decide, oh, I have more attack, so I'm going to attack with everyone else. But they're going to be, the generals are not all loyal. There are some people who are traitorous, so they're trying to, change the game somehow by confusing others, right? So these guys might send, suppose this guy, he might say, oh, let's attack to this general, but not to attack to the other. And of course, if there are enough such traitorous ones, they might, be able to control the outcome. So, and this is actually known to be like a foundation for the current important technology based on blockchain for Bitcoins and so on, because this has to do with distributed decision making and where security is very important. So even if some of the agents are not faithful, you may be able to keep things on track as the system should be doing. And related to randomization is it's interesting that for some setting in this Byzantine agreement problems, to make the algorithm scalable, meaning that you don't want to the running time to explode as the number of generals increase, randomization can be quite critical. So there are some results known as impossibility results, which means randomization must be introduced in the algorithm. And so that was one of the things that Roberto and I thought, oh, maybe we should try to come up with a control-oriented impossibility results in this type of systems. Now, another thing that I'd like to point out is that in the computer science literature related to these problems, often the networks or the connection between the agents or generals, they happen to be all-to-all networks, because in computer networks, it's wired, then it's not difficult that everyone exchanges messages to each other. So, which is not perhaps the most interesting setting in the kind of multi-agent systems that we have in mind, right? Start with autonomous driving cars or formation control of drones, and also wireless sensor networks. These are systems where the underlying network will be sparse, and it's very rare that they can be all-to-all. And that's actually the challenge, right? Because we want to make things as distributed as possible and not to have like a centralized controller and so on. Now, because the setting is distributed, they can be quite vulnerable to cyber attacks. And that was the motivation. Now, today, with all these applications related to cyber physical systems or Internet of Things, I think there is a very strong drive to address the security-related issues. So this Byzantine type algorithms, how can this be extended to the kind of systems that we are interested in? This is a important and interesting direction. So I guess there are different ways to formulate this problem, but we're going to stay with the agreement or the consensus problem that is has been quite a popular topic in our community. And when we say consensus, in our case, it's not binary. The agents will take a real value, right? Continuous. We're working in the continuous setting. So for example, these are the robots, and then they are going to exchange the information of where they are with the nearby agents, and they want to come together at some point, which is not decided in advance. However, if there are some cases which can happen through fault or noise, or even adversaries, if it happens that some of the agents misbehave, then we will not be able to have the consensus, at least in the way we initially wished. So what will be the way to avoid? And here, since we're interested in security, we like to think about adversarial agents to be behaving in the, like really in the worst case scenario. So we've been working on this problem for 10, 15 years or so. And we have this framework for agents to properly operate even under adversaries. And we have, you know, we work on this in a theoretical manner with, we have proofs. And as I mentioned earlier, one of the key issues that we like to address is how sparse can the networks be. So not all to all, but as we want to keep the number of connections between the agents to be as small as possible. And so here we'll be talking about a few things, but I'll start with the basics, and then I'll try to talk about how to increase the resiliency when we have more communication, and also when we have more computational resources. And this line of work, it has been studied a lot by different groups over the years. And I don't try to be exhaustive. These are the early works in the 2010s. It has become a very popular area in the last few years. So, but in these days, it was very nice because it's such an interesting problem, but there are not so many people working on it. So let me start with a very basic problem setup. So we have a network of agents, and each agent has a state. So agent I will have state xi, and so here we have the normal ones and the adversarial ones, which we call malicious agents. The normal ones will try to reach agreement in their states by interacting and exchanging their states over these edges. While the malicious agents can do whatever they want to, and we're interested in the case of the worst case, their behaviors. However, so malicious agents may know everything about the system. They may know how the agents are connected, what their states are, and so on. We put some restrictions, which is, I think they sound reasonable. So one is that everyone communicates only by broadcast. So even if a malicious guy transmits the data, this is going to be known to everyone. So he cannot send, like in that Byzantine, the general problem, I said, the general might send different messages to the neighbors, but this is not going to happen. I mean, we can study that case also, but for now, we will work with this simpler case. And if the agents are communicating by wireless communication, I guess this reason, right? The other assumption is that we assume that everybody knows that the maximum number of adversaries, the malicious agent in the network, is bounded, and they know the bound, the exact number, which is we call a small f. And maybe you know this through experience. Past, there were say 10% of agents became faulty or malicious, but perhaps not that. Then you can set this value. Okay, so everybody starts with their own states at the initial time. They want to come to consensus so that they have the same value at the end. This is, of course, basic goal. Now, what we want to require here is that the agents come to consensus, but they should stay close to where they started, right? So over the time, they're going to stay within this blue region, and they should not go outside, even if there is an adversarial agent, which might be, doing strange things in their states. So this is exactly the case where we want to avoid, for example, that the normal agents come to consensus, but outside the safe interval, and therefore this is not a safe situation. Okay. So this is just to state these things more formally. We have two requirements that should come to consensus in a safe manner. Now, for the updates, the agents will follow a fairly simple update rules for this case. So each agent, the normal ones, will follow this linear update rule based on its own value and the values received from the neighbors. These are going to be the relative difference will be weighted, and then we take the average to be added to the current state value and obtain the new one. Now, what do we do in the case of when we find malicious agents? This is going to be affect the choice of the weights and whose values will be used in the update rule. I'll be more specific about this in the next few slides. And the malicious agents can do whatever they want to. So it has an input to be added at each time step, but this can be chosen arbitrarily based on a lot of information if they want. Okay. Now, the class of algorithms that I'll be mostly talking about is called this mean subsequence reduced algorithm, MSR in short. And the basic idea is that the normal agents are going to ignore whatever data that will be received that are suspicious. So in this example we saw, the orange value is if it's way below the blue values, then that's going to be appear like an outlying value, so that can be ignored perhaps. And since everybody ignores some a subset of the values that they receive, this means that each agent needs to have more neighbors. So that means we'll have more connections in the network than the usual consensus. The algorithm is very simple, actually, and this is partially because we don't try to detect which agents are adversarial. And here's the algorithm described. So each agent at each time, they receive a number of messages from the neighbors. They're going to sort the values from the largest to the smallest. And since we know that among them, F of them may be malicious, so simply what they do is to remove the F largest and the F smallest, and then take the average, right, to make the update. So this means that at most, maximum, 2 F values might be removed. And in other words, that means that each agent should have at least 2 F neighbors, but this is probably not enough, right? You cannot just have a lot of neighbors to guarantee that we come to consensus. So we'll look at this through a simple example. So we start with this network, and it has 5 agents, and these numbers indicate the state values that they started with. And here, the orange one happens to be the largest value, and we'll say that this is malicious. Now we focus on this guy, whose value is 8. He receives 3 values from the neighbors over the edges, and the largest and the smallest will be removed. So in this case, values of 1 and 10 will be removed. So I indicated the edges and dashed lines. So there will be only one value 4 left. No, the normal agents will do the same. I follow this MSR algorithm. And at the end, the edges left are going to be these 3. And they can make updates based on what they receive from this agent with state 4. And this guy will not receive anything because he didn't have enough neighbors, but it's enough since we have a directed spanning tree, which is the necessary sufficient condition for achieving consensus for the usual normal case, right? So this shows, I guess, how the agents will make updates, and at least in this example, things seem to work. Now, how can we go beyond this example and make things more general? So as I mentioned, we want to have a network that has directed spanning trees. This will be like the minimal requirement, even if there's no malicious agents. And we will call this to be one robust. And we want to have a more general notion extending this. This is going to be called our robust graph. And this requires a little bit of explanation for the definition, but a little bit combinatorial. So we start with this notion of our reachable set, which is a set of nodes, including a node, at least one node having R edges coming from outside. So that means there's a node that have many incoming edges. Now we call a graph to be R robust, and this is the combinatorial part. We look at every pair of non-empty disjoint subset of the nodes, and at least one of the subsets is R reachable, having a node that has R incoming edges. Checking this is actually NP hard, so computationally a little bit involved, but this will lead us to a tight condition for the problem. Just an example for 2 robust case, this graph with 4 nodes happens to be too robust, a very similar looking graph may not be too robust anymore. So we have to be checking very carefully. And in our robust graph, it was enough to have one node that has our incoming edges. If we require this to be more than one, we come to this notion of S robust graphs. So in this case, S nodes have to have our incoming edges. I will not go through the details, but well, the result that we come is that agents using the MSR algorithm will reach resilient consensus if and only if, assuming that they're at most F malicious agents, right? The necessary sufficient condition is that the network is F+1 robust. And so this is a tight condition. And then the example that we just looked at happens to be 2 robust, which means that with F equals to 1, it satisfies this condition. So that example, which worked, it was not by chance, but satisfies the condition. Okay, so this was the basics for this class of problems. We have been extending this in different ways. And I'll start with this problem, which is related to what I talked about the works with Roberto. So so far, the agents were communicating with each other all the time in a synchronous manner. Now here, we will look at the case when the agents communicate asynchronously. So at different times, different agents might communicate. And so what happens is, in this example, there might be a malicious guy here. If these 2 guys update at a certain time, they might go closer to them, while these 2 guys, if they are at rest at this time, they're not going to move and stay there, right? But if the malicious guy knows when the other 2 guys will make an update, he might just as well switch his location, right? So that these 2 guys will follow this and go towards that direction, while these guys will stay if they're not making updates. So clearly, there are more ways for the malicious agents to make the moves, right? And this, as a result, it requires more connection in the network, especially for the deterministic case. So if the malicious guy knows when the agents make updates, there are more ways to misbehave so that everybody is confused. Now, interestingly, the situation changes when we look at the probabilistic case. And so this is the agents can decide when to make the updates in a probabilistic way, meaning that at each time they're going to decide, oh, well, maybe they'll roll the dice and say, oh, I got an even number, I'm going to make an update, or I got an odd number, so I'm going to just stay put. This way of communicating or making updates is known as the gossiping. Because you know, when you go to a party, you gossip, you might meet different people, talk about random things at random times. And this turns out to be a very effective way for maintaining security. So in this way, the malicious agent will not know when they make an update, so they cannot decide in advance how to attack. And this is turns out to be a very effective way. And especially in this resilient consensus context, the network connectivity required for this gossiping case is the same as the synchronous case. So we are recovering the original condition, and Roberto and I were very happy to call this to be, well, at least one kind of an impossibility result for this the problem. So we have this paper from 2018 that appeared in the Transactions of Automatic Control. This is, well, it happens to be the last paper that I co-authored with Roberto. But we started with this idea more than 10 years before this paper, and I was happy that we could somehow close the story with this. And then we have, beyond just the usual consensus, we have we worked with other kinds of problems. We might have more dynamics for each agent, or the communication, we might have event-triggered communication. And also we can work with leader-follower type problems where this light blue lines indicate how the leaders move, and how the blue lines indicate the followers who try to go together in a time-varying reference signal. But the idea is very similar, and we need to ensure that in these cases also that the graphs satisfy certain different conditions. We also worked with this synchronization problem based on the so-called pulse-coupled communication. So these clocks, when they come to 12, they make a beep or emit a light to communicate with neighboring clocks. And you see that they come to the synchronization. In this case, actually, the red ones, there are two. These are malicious, but we can extend the MSR approach to come to a tight condition, characterizing how many malicious clocks there can be. And in this case, it happens to be two. As I mentioned, the Byzantine problem originates in computer science. And I had a colleague in my university who was a specialist in this area. And he told us that if you're working in this area, there's a new class of adversaries known as mobile adversaries. So in this case, the total number of malicious agents may not change, but over the time, they might switch which agent to attack. So maybe this guy was initially malicious, but then the attacker decided to move to this agent, and so on. So this is a more adversarial setting. And the interesting thing is that when the malicious agent switches, right, the guy who used to be malicious, his system may have been modified, right, by the attacker. So when he recovers, whatever that's left in his memory, it may not be something trustable, right? So we have to figure out how to work with that situation. And when he recovers, if he's aware that he was attacked, then maybe he will decide to discard everything that he has and start fresh, and so on. So that's the kind of setting with the mobile adversaries. Okay, with the time remaining, I will briefly talk about how to enhance resilience in the original consensus problem. One is by using the so-called multi-hop communication. So far, when an agent communicates, his state was sent to agent 1 over the edge. So this is a one-hop case. Two-hop means that when an agent transmits its state to a neighbor, that neighbor is going to relay what he received. So agent 1 can receive the data of agent 4. That's 2 hops. So everybody receives more data from the that are relayed, right? And that seems to help to enhance the resilience. But on the other hand, if this guy happens to be malicious, right, he can modify what he received and then relay it. So there are more ways to attack. So it's not very clear if we're going to be doing better, at least not immediate. On the other hand, what's very useful in this context is that multi-hop allows us to have multiple paths for the data transmission. So his data can reach agent 1 through at least 3 different paths. And that's going to help us to increase the resilience. So just like I mentioned, agent 1 can receive agent 4's data through 3 different paths. And there can be different situations. One, for example, is that the state that comes through agent 3 will look strange, outlying, let's say. Then it's clear that agent 3 manipulated the data, right? And we can immediately say that we detected a malicious agent there. Another case is when all the 3 messages coming from agent 4 looks strange and outlying, although they all have the same value. Then there are at least 2 cases. One is that agent 4 is malicious, and then he's sending a strange value that are relayed by the normal agents. Another case is when the intermediate agents are all malicious, but this is perhaps less likely to happen because it takes 3 agents to realize this same attack. So by exploiting this type of ideas, we can extend the MSR algorithm to the multi-hop case and have, I'm not going to the details, but for this class of systems also, we have a tight condition for the network connectivity structure. And well, this turns out to be quite a powerful approach. And we have certain other extensions. So as I mentioned, detection can be possible when you have a multi-hop. And this is going to help us to realize more complex tasks for the multi-agents. For example, to compute the exact average of only the normal agents. And so whenever we detect someone is abnormal, then we have to take out the effect that that agent has brought into the system over the time. The conditions that I've been talking about is a bit, as I mentioned, it's NP hard to check the graph condition. And so we're often asked what happens if we cannot check, like if the network is so big, we cannot check if the conditions are satisfied. We had to check, we did a lot of simulations to show that by going from 1 hop to 2 hop, we can do better. And there's often a case where, 2 hop is enough, 3 hops will not improve the situation so much, and so on. Okay, the last part, going to be very quick, but MSR approach seemed to be very simple. We're just removing the largest and the smallest. Isn't there a way to do things better? And I think I'll just explain this idea for the vectorial case. So suppose this is a state space in two-dimensional, and we want to find a point where the state update should be based on these 6 points, and it should be inside the convex hull of formed by all the 6 points, and hopefully somewhere close to the middle. Now, we can do something similar based on MSR by applying MSR for each coordinate, but in that case, we'll not be able to find a point inside the convex hull, but it will be inside the rectangular, which may not be ideal. Now, if we know that one guy is malicious, right, then we're not going to include that point and make a convex hull based on the rest of the points, right? But if we don't know who might be malicious, we're going to do this for every case, right? And then take the overlapping area, which is indicated by that gray area, and make an update in that region. So this is a safe way for making updates. And this turns out to be actually quite a useful approach. Now, computing the intersection of these different convex hulls, it can be done, but computationally it can be expensive. So we apply this technique known as center points, which comes from computational geometry. And this is more or less like a vectorial version of the median of points. And that can be used for the updates instead of using this MSR technique. And we can derive graph conditions for different classes of problems based on this center point algorithm. And this gives a summary of different algorithms, the attacker models, state dimensions, and then the requirements for the topology. And it's quite clear that with center point, whether it's a static or mobile adversaries, we can do much better in terms of the robustness of the graphs. So this is an ongoing research at the moment. I think it's quite promising to go beyond MSR. Okay, so in this talk, I gave an overview on the framework for resident distributed algorithms. It has theoretical proofs. This is quite relevant for the cybersecurity of multi-agent systems. And I think it's quite interesting because, well, it's an interdisciplinary area for systems control and computer science. Computer science because of security, because of algorithms, distributed algorithms, and also some of the techniques we are using. And there are interesting questions that we like to address because it's multi-agent systems. There are a lot of different classes of problems that have been studied. We can make resilient versions of those. Also, another direction that I haven't been able to follow so much is how to incorporate learning techniques to enhance the resilience. Okay, I'd like to just finally acknowledge my collaborators, my current and former students, postdocs, and also, of course, Roberto. This is a picture taken in Osaka together with my former student, Meharanti Baji, and who was the co-author for the last paper that we wrote together. So I'd like to end this talk thinking about Roberto.